I think I'll start again here. Hopefully the camera won't flake out on us this time. So like I said, I'm sorry about the general disjointedness of what I just did in class. I have notes that if I could follow, it would have been more orderly. And I would encourage you to read my notes. I think when you do, you'll see it's a little bit more one thing at a time, you know. And again, the notes are incomplete, right? There's like a lot of like foundational things that could be built up there that I just haven't done. So I'm being a little bit, as we say, formal, right? Anyway, now moving on to section 1.4, which is on paths and curves. And so this is really crucial to understand carefully if we want to make sense of O'Neill going forward. So, but again, I'm still being a little bit n-dimensional here, and but you know, essentially in O'Neill, same thing, but for 3 dimensions, right? But anyway, here's definition 1.41, which is the definition for what we mean by a smooth parametrized curve in Rn. A smooth parametrized curve in Rn is a smooth function. What's that mean? Continuous means we have continuous derivatives of arbitrary order. Smooth function, alpha, and I'm using I as its domain, subset of R to Rn, all right, where I is an open interval. And what else? The point set, alpha of I, is a smooth curve. So notice that we're defining smooth parametrized curve to mean the parametrization, right? And the actual point set that it covers is the so-called smooth curve. A curve is a smooth curve if it admits a smooth parameterization. Of course, you could replace the word smooth with continuous or once differentiable or twice differentiable, all that kinds of other stuff. And in our study of curves in the next chapter, I say we'll study smooth curves with non-vanishing velocity, that is to say regular curves, all right? So before I get to defining velocity, let me just give us an example of a curve, all right? So example, I'll call this example 1. How about this? Alpha of t equal to, let's say, r cosine t, r sine t, mt, for t in the reals. Oh, let's say actually for t, an element of, let's say, 0 to infinity or something like that. There we go. That's an open interval. Of course, if you want it to be a finite curve, you don't have to let it go to infinity, right? But what is this? This is a smooth curve in R3, right? What is that? What did you say it was? Oh, yes, okay. It just so happens that yes sounds a lot like the name of the curve if you don't hear it exactly right. So let's see here. Where's alpha of 0? Alpha of 0 would be r, 0, 0. That's a point on the x-axis, about right here. Where is r, where is alpha of pi over 2? Cosine of pi over 2, 0. Sine of pi over 2 is 1, right? M times pi over 2, whatever m is. I'm thinking here m and r are positive numbers, right? But x is equal to 0, but y is r. And so it's like on the x, z, y plane. It's over here somewhere, you know? And you can continue on. And you'll go up and up, right? This is actually what's called a helix. This is the right circular helix, with radius r and slope m. That's just my terminology. I don't think that's like, I don't know if there's like a standard agreement that that's the radius and that's the slope. I think of that as the radius. If you were to take this helix, you could wind it around a cylinder with radius r, right, which has the z-axis as its center, right? So cylinder's just, the helix goes up around the cylinder like that. But there you go, that's a smooth curve. It's actually a very interesting smooth curve because if you think about different special cases, you can get a lot out of this example. What happens when you let m equal 0? What does the helix become if m is equal to 0 here? So I'm asking them the question, what happens if m equals to 0? What does the helix become? Two-dimensional, right? It squashes down to a circle, right? The projection of this helix onto the xy plane is actually just the circle radius r. So you can, in some sense, think of the helix as just like taking a string that is set around the circle infinitely many times and just kind of taking that string and lifting it up and just sort of looping it around a cylinder if you want. Oh, like a slinky. Yeah, like a slinky. Perfect. Yeah. Another kind of weird extreme case to think about is what happens if r is equal to 0? If r equals to 0, you're just on the z-axis. It's a straight line. So in the limit that r tends to 0, we go from the helix. So a helix in two different limits is a line or a circle. It's a very interesting curve in that sense. You can learn a lot about differential geometry from studying a helix. Okay, so definition. Velocity. Velocity of smooth curve. Alpha. And I should say parametrized smooth curve alpha. Okay, because we're defining the velocity of a parametrized smooth curve. Excuse me, a smooth parametrized curve. Alpha prime of t. So here, I mean, alpha is again I subset of the reals to Rn. Then alpha prime of t is an element of the tangent space at alpha of t of Rn defined by. So remember what the tangent space, to alpha t of Rn, how did we define it? It was a differential operator, right? So here's the definition. I guess I should, before I do that, let me clarify something. Before I say defined by. I'll just put a period here. Observe alpha is equal to alpha 1, alpha 2, alpha n, right? Where alpha upper I themselves are functions from, let me say alpha upper j. Alpha upper j are functions from I, the subset of the reals, to what? Come on. The component functions are themselves just plain old ordinary functions from functions of time, and their output is just real. Like here, alpha 1 of t was r cosine t. Alpha 2 of t was r sine t. Alpha 3 of t was m times t. Those are the component functions. Okay. Define. Alpha prime of t is equal to alpha 1, d alpha 1 dt partial x1 at alpha of t plus d alpha 2 dt partial x2 at alpha of t d alpha n dt partial xn at alpha of t. So the velocity of a smooth curve is a differential operator, right? It's a differential operator. It's in fact a derivative where the coefficients of the partial derivatives are given according to the rates of change of the components to the curve. This is really no different than the definition we gave for velocity in Calculus 3. It's just what velocity looks like when instead of using static vectors, I, j, k for the unit vectors, we're using partial x, partial y, partial z for the unit vectors, right? Like this is exactly what we would seen for the velocity in Calc 3. It's just now we're using the partial derivatives for the basis vectors of our vectors. All right, now, furthermore, a little bit more here. Also, alpha is regular curve if and only if alpha prime of t is not equal to 0 for all t in the domain. I sometimes call a regular curve a nonstop curve. See why I would call it a nonstop curve? It's a nonstop curve if its velocity is always non-zero. It's always moving. If you allow curves, if you allow parameterizations of curves to do things like stop and then start again, it just throws the calculus into chaos. Like it's no good. everything analysis-wise you want to say, just it all falls down. So we definitely don't want, we want our curves not to stop. It's, of course, useful to look at what happens. Remember, to understand these operators, we like to think about what happens when we act on a function, like in your homework, right? So what happens if we let alpha prime of t act on the function f? What happens there? Right. I mean, we differentiate with respect to x1, with respect to, I mean, we just put f here, everywhere. So if you'll forgive me, I'm going to write it in a more compact notation. Sum j equals 1 to n of d alpha j dt partial f partial x upper j evaluated at alpha of t. But the thing is, there's a chain rule in Calculus 3. And the chain rule says that, in fact, that is nothing more than the derivative with respect to time of the composite of the function f with the curve alpha of t. This is nothing more than d dt of f composed with alpha of t by the chain rule. And if you write that using prime notation, it is even more slick. This is f composed with alpha prime of t. So just to reiterate, this is a theorem, if you will, alpha prime of t acting on the function f is nothing more than f composed with alpha prime of t. The main step here was chain rule, multivariate chain rule. So this was my proposition 1.4.3. And I say, okay, so what is this saying? What's this theorem saying, like, in words? It's saying that when we let the velocity vector of a curve, right? When we let the velocity vector of the curve act on a function, what is that value telling us? It's telling us the rate of change of the function if we restrict the function to the curve. It's telling us how the function changes along the curve, right? So if we could find a function which doesn't change along the curve, what should happen when we hit it with the velocity vector of a curve? Like if you could find a function that was somehow constant over the curve, when you hit the velocity vector on the curve, you ought to see that the velocity vector on that function should just be 0, right? Like, let's try this intuitive idea out on the helix. What is the velocity vector of the helix? I'm going to erase a little bit here. We don't need the picture, right? Well, I'll leave the picture. Well, thank you. But alpha prime of t here is minus r sine t partial x, right? And I can actually, I'm going to erase the definition of velocity now because I think we're past that. In fact, I'm just going to erase everything except for the theorem. Okay, so velocity of the helix minus, so the derivative of r cosine t is minus r sine t, partial x, r cosine t, partial y. I'm ignoring the example in the notes, by the way, because I think what we're doing right now is more interesting. So let's do that. Besides, you can read the notes later. You'll have another example of questionable pedagogical use. But anyway, so there you go. This is the velocity field to the curve, right? Let's take it for a spin. What happens if we calculate alpha prime of t acting on the z function? I mean, I expect that we're going to get something non-zero. This should describe how the function is changing in the z direction. Right? Don't make too much of it because we'll soon talk about a reparametrization of the curve, and if we reparametrize the curve, we would get a different velocity field. Right? Like if you went around the helix like this versus if you go like this, those are going to give different velocity fields. But it could have the same shape. I mean, well, anyway, we'll get to that in just a second here. What's this work out to? So think about hitting Z on this. What do you get? It's this is 0. This is 0 when it hits Z. The only thing that survives is the M. I'll write down one step. M partial Z, right? So M.
Would we differentiate as we did in terms of T?
Well, yes, I differentiated each one of these component functions with respect to T, like alpha prime of T in 3 dimensions is d alpha 1, I guess upper 1, d alpha 1 dt, partial x, plus d alpha 2 dt, partial y, plus d alpha 3 dt, partial z. That's the definition of the velocity curve, the velocity to a curve in dimension 3. Unfortunately, I just erased the general definition. But there it is in 3 dimensions. That's what I did. I differentiated this with respect to time, with respect to time, with respect to...
we were referring to N, right?
Yeah. But that's what it looks like for 3. For 2, we just have alpha 1 and alpha 2. But, okay, great. So apparently the z function is changing at rate m along this curve in some sense. How about the x function? How is it changing? In that one, this is 0, and you just pick up the minus r sine t. So that says sometimes x is increasing, sometimes x is decreasing. But that's what happens on the helix, right? X is decreasing, right, until it gets back onto that back part, and then it's increasing up until it gets to like here, and then it's decreasing, and then it's increasing, and then it's decreasing. Because the sine of t goes back and forth, plus minus, according to that pattern, right? And if we did y, what would we get? Same, yeah. Can you guys tell me a function which would be constant on the helix?
Like in 3 dimensions or 2?
Like which function, if I hit the velocity vector field on that function, is going to give me 0? I mean, there are many that would do that. But this one in particular I have in mind. How about if we took, I'm pretty sure that x squared plus y squared is going to give us 0. Let's see how that works. Let's try it out. F equal to x squared plus y squared, how that's going to work. Now we got choices here. But I guess I'll just go straight with the, let's see here. So we got, I'll write it out. Minus r sine t. And then we do partial x at alpha of t, right? Of x squared plus y squared. Plus r cosine t, partial y, evaluate at alpha of t afterwards, of x squared plus y squared. And then there's the z term, which is 0, right? So I'm just going to write 0. So what is the partial derivative of x squared plus y squared? It's 2x, right? The partial derivative with respect to y of x squared plus y squared is 2y. But how does it work? Are we just saying differentiate? We're saying differentiate, and then, after you're done, evaluate at the curve. See that evaluation bar? So that means that I do minus r sine t times 2x such that x equals to what? Y equals to what? I mean, I'm saying evaluated alpha of t. What is alpha of t? It means x is equal to r cosine t, right? Y is equal to r sine t. So what do we got? We got ourselves a minus 2 r sine t cosine t, r squared sine t cosine t. Lo and behold, plus 2r squared cosine t sine t, also known as 0. And I would argue this makes sense because this helix is wrapped around the cylinder, which is defined by x squared plus y squared equals to r squared. And that doesn't change, no matter what time is. Oh man, I was trying to get away from the notes. This is my example 1.4.5. I am a creature of habit. I can't escape my own examples even when I don't read them. Ay, ay, ay. So disappointing. I mean, it's fine. I think this is a great example, actually. I'm really happy about this example. Okay, so next up, we talk about a reparametrization of a curve. This is a very important idea in this course. What is a reparametrization of a curve? Change the components to make it continuous if it's not. Kind of like that. We change the, it is what it kind of sounds like. It's like change the parameter, and it doesn't have to be for any particular reason. It's just it's a changing of the parameter of the curve. So in O'Neill, he tends to talk about t. He actually, and this is a good idea. This is like a good intuition. What is t? You know, in Calculus 3, you ever teach Calculus 3, you'll be faced with the question invariably, but what is t? Right? Because we know what x is, we know what y is, we know what z is, right? But what is t? T is time. But it doesn't have to be, right? I mean, it's a parameter, really. And so a good answer to that, actually, is t is the coordinate along the curve. So t, you could think of the curve as being the t-axis, actually. Right? That's not a bad intuition for what t is. I also think it's a label at each point of the curve, but that's just saying the same thing. So a reparametrization of the curve is a relabeling of that parameter along the curve according to a specific rule. And here's the definition. And I'm going to put it here because we're good enough place for it. So definition. Alpha, a parametrized curve. I'll say smooth, parametrized curve. I should have come up with an abbreviation for that, you know. If, here it is, h, which is a function from j to I, all right, is a smooth function on an open interval j, then what? Then beta equal to alpha composed with h, which is a mapping from, well, j to Rn, is said to be a reparameterization. Well, it is a parameterized curve, which we call the reparameterization of alpha by h. Reparametrization that's a mouthful of alpha by h. So notice I don't assume that the reparametrization covers the whole curve. Like, it is possible to have a reparametrization in this way of thinking that covers just some part of the curve. It could be that the original helix, we could chop 0 to infinity down to like 0 to 6 pi, you know? 0 to 6 pi would cover three wines of the helix. A reparametrization might only cover 2 wines. That's possible in this definition, because we don't assume that it covers the same smooth curve. Okay, so then naturally, what you'd like to do, of course, is to calculate the velocity of a reparametrization and relate it to the velocity of the original curve. Well, how does the velocity of a reparametrization relate to the velocity of the curve? So the question we're asking is, what's the deal with beta prime? And I guess we're using, I use S for the new variable. S. So here, beta of S is equal to alpha of H of S. Intuitively, like if you want me to, you could say this, basically the idea is T is equal to H of S. All right. So let's calculate beta prime of S. Well, that is DDS. Well, fine. So apparently the sum, right, j equals 1 to n of what? D alpha sub j, upper j, of H of S with respect to S, partial, x upper j at beta of S by the definition of velocity, right? That's what we do. Now this alpha j of H of S, I'm making the observation, the jth component of the reparametrization is the jth component of the original curve composed with H. That's how parameterization, that's how it would work. So then by definition of velocity, I have that derivative, right? But then chain rule. I use the chain rule. And if you differentiate a composite function, how does it work? You do the derivative of the outside, evaluated at the inside, times the derivative of the inside, right? In other words, by the ordinary chain rule, applied n-fold times, this is nothing more than alpha, well, notation, fine, d alpha j dt times dh ds. Partial x upper j and beta of s. Now I'm being a little bit sneaky here. When you write d alpha upper j dt. What that means is to differentiate the alpha j function and to evaluate it at t. Like this notation, what I mean by this is alpha sub j, take the derivative of that thing, upper j rather, prime, and evaluate it at t, but what is t? H of s. So like this, I literally mean that. And I probably should just write that. I don't know, maybe I should just write that. But anyway, the larger point here is there is this dHds term, and does that depend on j? It does not, right? So can we, that's a constant, it's in every term in the sum, so we can pull it out by properties of finite sums. And we just have dHds times the sum. And I'm sure hoping what I'm about to write down here, it just kind of stands out as being something. D alpha j dt partial xj at beta of s. What is beta of s anyway? Beta of s. Oh, alpha of h of s, I guess. Fine. Let me be really obnoxious here. D alpha dt of h of s. I could write it that way. There. Now I feel like I'm being more honest now. Beta of s is alpha of h of s. Notational quagmire. What is that? That is the velocity vector of alpha at time h of s. So that's like, our notation for this would be alpha prime of h of s. And indeed, that's the theorem. That beta prime of s is equal to dh ds times alpha prime of h of s. Theorem beta prime of s is equal to dh ds times alpha prime of h of s. All right. There you go. So long story short, what does this say? This says if we reparameterize the curve, the velocity does what? It just gets multiplied by a scalar, right? If we compare the same point before and after the reparameterization, right, if we match the value of t to the value of s as appropriate, if we look at the same actual literal point on the curve, the velocity vector is going to have the same direction. It might just have a different magnitude. Am I right or wrong? Will it have the same direction? What critical fact do we need to know about this h function for it to have the same direction? Well, yeah, h could be different things. But my question is, in order for beta prime of s to be in the same direction as alpha prime of h of s, what do I need to know about dh ds? And it has to be what? It has to be positive. If it were negative, this would point opposite the direction of that. So if we care about the direction of curves, we have to be careful for our reparameterization to be increasing. If it's a strictly increasing function, it will have a positive derivative and we'll be good to go, right? So, it's a new noise, right? Now, let's see here. something maybe I mentioned it in the notes and I've just neglected to do it here, but we have vectors now that are partial derivative, built from partial derivatives, right? What else did we do with vectors in calculus 3? We calculated the length, we calculated dot products between them, right? But certainly we calculated the length. What would the length of a vector field be? Or what was the length of a vector in like this crazy new world of what's the if I mean let me just give you a definition. Definition: if v is equal to the sum j equals 1 to n of v upper j partial xj, like that, then the length of v is nothing more than the square root of the sum j equals 1 to n of v upper j squared. So same as usual. We can just use the components to calculate the length, just like we did before. All right? And what we're going to say is, the length of the velocity vector for a smooth parametrized curve has a name. What's the length of the velocity vector for a smooth parametrized curve? Yes, the magnitude of the velocity, what do we call that? It has a name. I'll write it down here. So like in 3 dimensions, the magnitude of alpha prime of t is the square root of d alpha 1 dt squared plus d alpha 2 dt squared. Man, I really cannot write at this level. Sorry about the butchering of my font is completely degraded at this particular height. Ugh, horrible. Anyway, the square root of the x component of velocity squared, the y component of the velocity squared, plus the z component of the velocity squared. This is the magnitude of the velocity. We also call this the... It is that. This is the speed. The speed. Speed and velocity are not the same thing. Speed is a scalar, velocity is a vector. If the speed of the curve is 1, we call it a unit speed curve. All right? So, it's an interesting problem then to ask the question, okay, we got this helix, right? Can we reparameterize this curve to give it unit speed? You can always do that. You are right, but why is that true? You have to make it equal to 1, right? Did it in Calc 3. What parameter, I guess my question is, what parameter do you use to make it have unit speed? Possible field to 1 in every direction. Oh, these have to be equal to 1. I mean, I agree with that. That you're not wrong. But we're dancing around the issue here. And so we're missing a definition. All right, let's give a definition. Yet another definition. All right, definition. Given alpha I subset of the reals to Rn with, let's say, T naught an element of I, the arc length based at t naught is defined to be let's say s of t equal to the integral from t naught to t of the magnitude of alpha prime of, I need to use some other letter, let's say tau, d tau. So the arc length is defined to be the integral of the speed along the curve subject to some base point. What are the properties of arc length? Like the critical property of arc length, I mean, there's a couple of things you can observe right off the bat. Like, first of all, arc length of t naught is what? Like s of t naught is what? This is pretty low-hanging fruit. S of t naught equal to what? Right, but that's the integral from t naught to t naught, so what would it be? 0, yeah. And by the way, there's something that's a little bit, like the definition I gave was for an open interval for the domain of the curve, but push come to shove, we don't mind using the domain to be a closed interval. The reason that the definition is given as open interval, I think, is to avoid certain pathologies, which I don't want to talk about, and O'Neill doesn't want to talk about. But anyway, usually, I mean, more often than not, we don't force I to be an open interval. We let I be a closed interval. And more often than not, you're going to let t sub naught be the left endpoint of that interval. That's what we typically do. Like it would almost certainly be used, I would probably, I mean, what I'd like to do here is just say, you know what, I'm going to include 0, and that's where I'm going to start the arc length function for the helix. We'll get back to that in a second. But first of all, it starts at 0, and then it's an increasing function. Strictly increasing function for a regular curve. Why? What happens when we calculate ds dt? What theorem do we get to call on? We're differentiating an integral with a variable bound. Fundamental theorem of calculus, part 1. That is the magnitude of alpha prime, not of tau anymore, but of t. Right? And check this out. If it's a regular curve, alpha prime of t is non-zero, which means that the magnitude of alpha prime of t is non-zero. In fact, it's the length of a vector, right? So this is straight up positive. And we know from calculus 1, if you have a velocity, if you have a rate of change which is positive for all time for your function, that indicates that the function is strictly increasing. Right, so ds dt, in other words, arc length is strictly increasing. And so that's pretty nice. And so, yeah, if we use arc length to parameterize the curve, in other words, in some sense, this is kind of a cheat of notation, but if we set t equal to s, we essentially end up with ds ds, which gives us 1. But let's see here. Now, so you're right, you can always do it, right? Because if you have a regular curve, you can do this integration, and you can define the arc length like this, which means, in principle, if you have a curve parameterized by time to start with, you can trade time for arc length, right? I mean, we'd like for that. I mean, in theory, that is true. But in practice, to actually implement this, you have to be able to solve the formula for arc length for t. And in order to do that, you actually have to be able to put pen to paper to do the integral for the arc length. You guys remember integrating arc length, Calc 3? How many curves can you actually complete the arc length integral for? Like there's just a handful of them where that square root gets a square under it and magic happens and you can do the integral. It's actually pretty hard for an arbitrary curve. This is one of those things where it exists pragmatically, but in actual practice, it's hard to actually put into explicit practice the parametrization of a curve with respect to arc length. So yes, but it's theoretically useful because we can always, at least in theory, say, suppose I have an arc length parametrized curve. And that's very nice because it's geometric, it's intrinsic. There's just one arc length function. Once you pick a point on the curve, the arc length function is unique. It's something geometric about that curve. All right? So let's find the arc length for this helix, you know? Let's do it. What is it? I'm going to go ahead and erase the definition of reparametrization because I don't think we need it. So what is the, and by the way, well, fine. So for the helix, the length of alpha prime of t is what? So we've got minus r sine t, r cosine t, m squared. The speed is a number. Sorry about my handwriting.
It's going to pop out an r, right? Should be r plus m squared.
I trade your r for r squared, and we have a deal. So r squared plus m squared is the speed. There's the speed of the helix. In fact, this helix is actually very special. It is a constant speed helix. The speed is constant, even though the velocity is not. The velocity is always turning. Turn, 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 right? Yeah, it's turning in such a way that the speed stays constant. It's kind of neat. So the arc length here, and I'm gonna base the arc length from 0 because I don't want to be weird. So integrate from 0 to t of the square root of r squared plus m squared, right? D tau. Yeah, this is, I mean, we're integrating a constant. You can pull the constant out of the integral, right? Pull that out, integrate d tau. Integral d tau is tau. And so tau evaluated from 0 to t is just t. So the integral, it's just t times the speed. It's just straight up t times the square root of r squared plus m squared. So in this like super nice case, we can solve the arc length equation for t. It's not a big deal. What is it? T equals to what? Yeah, s divided by the square root of r squared plus m squared. I hope you don't mind that I've done the helix in terms of r and m. I could just as well have put r equal to 2 and m equals to 3, but I think we gain a lot by keeping the parameters because we can think about limiting cases if the fancy strikes us. And listen, that is that h of s thing we talked about. This is the quote-unquote h of s, the dreaded h of s in the definition I just erased. There you go. That is the reparametrization formula, which will reparametrize the helix to give us unit speed. So, almost done. So, great. Sorry, picture. It's got to go. Don't forget these. We need to keep these with us the rest of the semester. But I hope you realize that they're really not new. Those are the same definitions for velocity and speed we had in Calc 3. They're just now in our partial x, partial y, partial z madcap differential notation for vectors. So great. Beta of s is alpha of h of s, right? But in this case, that's alpha of s over the square root of r squared plus m squared. So specifically, beta of s is equal to r cosine of s divided by the square root of r squared plus m squared. R sine of s over the square root of r squared plus m squared. And then m s over, you guessed it, the square root of r squared plus m squared. So if you're like me, you start to get tired of writing the square root of r squared plus m squared everywhere. But there you go. That's the unit speed parameterization of the helix. Now, I would argue, because the arc length has an intrinsic geometric meaning, right? It's setting the rate of change of the curve with respect to length. You know, it's really saying that as you lay the parameter down on the curve, it has the meaning of length laid along the curve. It's setting a scale for the coordinate along the curve. And so because of that, if I was to calculate the velocity vector of this unit speed curve, and I was to go back and do those velocity acting on function calculations we did earlier, I would now take more stock in them as having a meaning, a sort of absolute meaning. But anyway, there it is. And you can calculate the velocity of this. What happens? When you calculate the velocity of this, you have to differentiate with respect to s, right? When you do that, what happens? Chain rule pulls out this guy on every derivative. But then everything else remains the same. And so when you calculate the length, you get this in the numerator divided by that, which gives you 1. Like you can calculate the velocity and calculate the speed. It has length 1. All right, so yeah. And so that brings us to section 1.5, which is on the push forward or differential of a map. I'm going to take a 5-minute break, and then we'll start again.